So as I've said, we are going to learn about different rules for taking derivatives of different types of functions. Yesterday we saw that if you just have a sum or difference of terms, you take the derivative of each term separately, and that gives you the derivative of that function. But then we also talked about sometimes you're going to have a product that you need to take the derivative of, or a quotient that you have to take the derivative of, or maybe it's a polynomial or an expression raised to some power that you have to take the derivative of. So we need rules to deal with those scenarios. And so today we'll learn about the product rule. If f and g, which represents functions, are differentiable, then so is f times g. And the derivative dy by dx of f times g can be found by taking f and then the derivative of g. So taking the first function by itself, multiplied by the derivative of the second function, plus the second function times the derivative of the first. And in this case, it doesn't really matter what order you do these two steps in. You can take, as your first step, take the second function and the derivative of the first, and then add the first function times the derivative of the second. It doesn't matter. Okay? But that's what we use to differentiate a product. So in other words, the derivative of a product is the first factor multiplied by the derivative of the second factor plus the second factor multiplied by the derivative of the first factor. So we're going to prove this. So capital F at x is f at x times g at x. So we can find an expression for the derivative, f prime x, capital F prime x. And we can do that by using that limit formula that we used when we first started derivatives. So this will be the limit as h approaches 0. So we're looking at this f at x times g at x. So remember, the first step is to replace, wherever we see the x, we replace it with x plus h. So it'll be f at x plus h times g at x plus h minus f at x, which is the original function, f at x times g at x, all over h. So all I've done is I've taken my original expression, which is f at x times g at x, and I've used that limit formula that we've been using, which we now know can be used to find the derivative of a function. Now, there's a step that we're going to do here because we need to do something to get rid of that h on the bottom, okay? And so there's a step that we're going to do here, and that is we're going to add and subtract f at x plus h, g at x from both. Thanks. Now, you wouldn't be expected to know this. This is just what we need to do for this proof. So again, we're going to add and subtract f at x plus h in the numerator. F at x plus h times g at x. Let me do a better job of writing that one. So again, you wouldn't be expected to just know that this needs to be done. This is just how we're going to do this proof. And so we haven't really changed anything, because when you add something and then immediately subtract something, they would technically cancel each other out, right? So we haven't really changed the value of the function because we're adding and subtracting the same value. But here's what we're going to get next. So we've got the limit as h approaches 0. We've got our f at x plus h. We have our g of x plus h. Remember, we're going to add and subtract that f at x plus h, g at x to the top. So here's where I'm going to put the subtraction part. Followed by the addition part. And then the remainder of the numerator was the minus f at x, g at x. And so now I'm going to do some factoring by grouping. So I'm going to group those first two terms together as well as the last two terms together. Factoring by grouping. And there is a common factor in that first group of f at x plus h. There's a factor of f at x plus h in both of those terms. So now I'm going to have the limit as h approaches 0. And again, I've got f at x plus h as a common factor, which if I take it out, it'll leave us with g at x plus h minus g at x. And what also I'm going to do here is, instead of putting the whole thing over h, I'm going to take both of these expressions I get when I take out a common factor and just put those over h separately. So it's like I'm breaking it up into two terms instead of one long term. But they would all have the same denominators. The two terms would have the same denominator. And as we said, in that second grouping, those last two terms, there's a common factor of g at x to take out, which would leave us with f at x plus h minus f at x all over h. Now, when we are taking the limit here, remember we saw about those principles of limits. We can break up the two parts if we want and take the limit of each part separately. So we did this when we started evaluating limits for the first time, where we broke it apart. We took the limit of each term that made up the expression. So that's what we will do now. My next step will be to say, okay, I've got the limit as h approaches 0 of f at x plus h times the limit as h approaches 0 of the next part plus the limit as h approaches 0 of the next part, which is just g at x, times the limit as h approaches 0 of f at x plus h minus f at x all over h. And if we look at the very top to see what we started with, f at x plus h would represent f at x. because when you can evaluate this limit by letting h equals 0, right? There's no denominator for that part. So you can evaluate this limit by letting h equals 0, and you're just left with f at x. Also, this expression here, the limit as h approaches 0 of g at x plus h minus g at x over h, well, that is the derivative of g. If you just have that function g at x and you want to take the derivative of it using that first principles formula, this is what you would write. You would write that expression, the limit as h approaches 0 of g at x plus h minus g at x over h. That would be the derivative of g. Plus, again, this next part here, the limit as h approaches 0 of g at x, there is no h there. So it doesn't matter what h is, this will always be g at x. And the last part, if you started with y equals f at x and you wanted to find the derivative of f prime x using the limit formula from first principles, you would have that expression right there. So that is the derivative of f at x. So there's our proof for that product rule. You're never going to be asked to do this, okay? But now you see where it came from. And the trick to doing it was, again, adding and subtracting that f at x plus h times g at x to the top. So it doesn't change the expression, but allows us to put the terms together so that we can get to that expression in the end. So you'd never be expected to know just to do that. It's only being done to show you the proof. Okay? And you will get a formula sheet with all of these equations on there, or these rules on there. Okay? So you're never going to have to memorize them because you'll have a formula sheet for any assessments that you have. So this says to differentiate the following. Now, in some cases, it's probably easier to multiply it out first, especially in these first couple ones. Probably easier just to multiply it out first, and then you can differentiate term by term. So for this first one, we'll do it both ways. So we'll start with method 1, where we will multiply it out first. So that'll give you 2x to the 5th plus 3x to the 4th minus x cubed. And then dy by dx, using the rule we saw yesterday, would be 10x to the 4th plus 12x cubed minus 3x squared. So there's the derivative. By multiplying it out first, by simplifying first, and then just taking the derivative of each term. Method 2, though, if we're going to use the product rule, dy by dx, could be found by taking the first factor of x cubed and multiplying by the derivative of the second factor, which would be 4x plus 3, plus the derivative of the second factor, the derivative of the first factor, which is 3x squared, times the entire second factor. So if you multiply these out, you'll get 4x to the 4th plus 3x cubed plus 6x to the 4th plus 9x cubed minus 3x squared. 4x to the 4th plus 6x to the 4th gives us 10x to the 4th. 3x cubed plus 9x cubed gives us plus 12x cubed. And then you have the minus 3x squared at the end. So either way, you get the same answer. And in some cases, it'll be quicker to multiply out and then differentiate. Certainly in this question, that was the case. Okay? So the same thing would work for question 2. We can multiply it out first and then differentiate. So if you multiply this out, you will get 6x to the 5th. The outer product would be minus 2x to the 4th. The inner plus 15x squared. And the last term would be negative 5x. And then the derivative, f prime x, would be 30x to the 4th plus 8x cubed plus 30x minus 5. So that would be doing it the first way. Simplifying the expression first and then taking the derivative of each term. Right, and what would it look like if we use the product law? Exactly. Really. So the first factor times the derivative of the second, which will be 6x minus 1, plus the derivative of the first factor, which would be 6x squared, times the second factor. Remember, the derivative of a constant is always 0. So when you take the derivative of that plus 5, a constant, it is 0. So this is f prime x, the first step. So we'll now multiply everything out here and collect our like terms. The front terms will be 12x to the 4th. The outer product's minus 2x cubed plus 30x minus 5 plus 18x to the 4th minus 6x cubed. Sorry? Yeah. So 12 and 18 x to the 4th will give us 30x to the 4th, which we needed. Negative 2x cubed, take away 6x cubed is negative 8x cubed. So I've got a mistake up there. I have to check. Yeah. So let me finish this off and then we'll go back and fix that. So that's negative 8x cubed. And then we have our positive 30x and our minus 5. So negative 8x cubed is correct. 6x to the 5th. Yeah. Okay, so there we go. For question 3, again, this will work both ways, but I'm going to do this one using the product law. And also, we have to write that root x as a power. Okay. Square root means power 1/2. So the first factor times the derivative of the second, which will just be negative 3, plus the derivative of the first factor times the second factor. First factor times the derivative of the second plus derivative of the first times the second. And it doesn't matter what order you write these in. So this will be negative 3x to the half plus half of 2 is 1x to the negative a half. And then when you multiply the 1/2 x to the negative half times negative 3x, 1/2 times negative 3 will be negative 3/2. And then when you multiply the x's together, you add the exponents. Negative a half plus 1 is positive a half. Now we do have like terms here, right? The first term and the last term are both powers of x to the power half. So we can combine them. If we have negative 3 and subtract 3/2, this negative 3 would be like negative 6/2. Take away 3/2 is negative 9/2. X to the 1/2 plus x to the negative a half. And there's a couple things here that we could do. We could factor this. Remember, we saw this on the very first day. When you're looking for a common factor and looking at terms that involve rational exponents, we always take out the exponent that is the smallest. There would be a common factor of x to the negative a half here, which would leave us with negative 9/2. And when you divide x to the half by x to the negative a half, you subtract the exponents, and it would be x to the 1. That second term of x to the negative half divided by itself is just 1. So you could write the answer like that. Normally we don't leave answers with negative exponents, so we could make this x to the negative half being positive by moving it from the top to the bottom. And maybe write it as a root. And then you could also rationalize this by multiplying top and bottom by root x if you wanted to. Okay, so there's lots of things that can be done, and if you're checking answers in the back of the book, they may do some of those things. So just be aware of that. All right. Now, this next one is a little bit different. Okay, the function f at t is at minus c times at squared plus 3c. But the part at the beginning where it says f at t tells us that the variable is t. That means any term that doesn't have a t in it is a constant. And we know that when we take the derivative of a constant, you always get 0. So you have to realize that for this one. When it says f at t equals, that's telling us that f is a function of t. That means t is the variable. That's the part that's going to change. Any term that doesn't have a t, which would be the c and the 3c, when you differentiate those terms, you're going to get 0 because they're constants. T is the only variable here that would change. So, f prime t, using the product law. The first factor times the derivative of the second factor, which would be 2at, plus 0 if you want, because when you take the derivative of 3c, that's going to be 0. So that's the first factor times the derivative of the second, plus the derivative of the first factor, which will just be a. Because when you take the derivative of this first factor, again, this is at to the 1. You would differentiate this by using the same law we have been using. The 1 comes in front times the a. The power on t decreases by 1 to 0. T to the 0 is 1, so you just get a. The derivative of the c, again, will be 0 because c is a constant. So there's the derivative of the first factor times the second. So whenever you get a function that's just not in terms of x and y, you need to take note of this, right? Look at what variable is changing. That's the variable that'll be inside the brackets after the f. So you'll be differentiating those terms that contain the t, like we normally do, but any term that doesn't contain t would be considered to be a constant, and the derivative of the constant is 0. So this is going to give us 2a squared t squared minus 2a tc plus a squared t squared plus 3ac. And we have one set of like terms here, the 2a squared t squared and the plus a squared t squared can be combined. That'll give us 3a squared t squared minus 2a tc plus 3ac. So there is our derivative. So we're asked to find the equation of the tangent line to the graph of that function at the point 1, 5. So we know that we can find the slope of the tangent by taking the derivative. And we have two options here. We can multiply it out first and then differentiate after, or we can just go straight to the derivative, which I'm going to do just for the practice of using the product law. So again, it's the first factor times the derivative of the second factor, which would just be 6x squared, plus the derivative of the first factor, which will be 6x, times the second factor. So this will give us 18x to the fourth plus 12x squared plus 18x to the fourth minus 6x. I'm sorry, not 18x to the fourth, 12. 6 times 2 is 12. So that'll give us 30x to the fourth plus 12x squared minus 6x. So there's our expression for the derivative. And the slope of the tangent is the value of the derivative at the point of tangency. The value of x at the point of tangency is 1. So f prime 1 will give us the slope of the tangent. So this will be 30 plus 12 minus 6. 42 take away 6 is 36. So that's the slope of the tangent. And I'm going to find the equation using point slope. We could also just use y equals mx plus b. Remember, most equations have an x and a y in them, so that's where the x and y come from, Brighton. But y1 will be 5. That's the y coordinate at the point of tangency. Again, m, our slope is 36. x1 would be 1. And if we wrote it in slope-intercept form, it would be y equals 36x minus 31. In general form, that means everything on one side equal to 0 on the other. The order is the x term, the y term, the constant equals 0. No fractions or decimals, and the x term positive. So that's why we would bring the y over to the right. Right, so there's the equation of that tangent line. All right, think that's it. Yep. So tomorrow we'll learn about the quotient law, your assignment, which you are going to hand in for marks on page 92, numbers 2 through 6. I'm going to hand this one in. Okay?